Your microcontroller might be a genius with numbers, but the real world doesn't speak in neat binary code. Temperatures, light, sound, they're all analog, continuous, and a bit messy. Enter the analog to digital converter, or ADC, the gadget's built-in translator. Without it, your device would have no idea what's going on around it. So how does an ADC translate the real world into numbers? First, it takes samples, tiny snapshots of the signal at specific points in time. Then, it assigns each snapshot a value using resolution, measured in bits. Think of resolution like a ruler's markings. An 8-bit ADC has 256 steps. A 10-bit ADC has 1,024 steps. More bits equals smaller step size equals finer detail. For example, measuring voltage from 0 to 5 volts. 8-bit, each step approximately 19.5 millivolts. 10-bit, each step approximately 4.88 millivolts. Higher resolution means your readings are smoother and closer to reality. Resolution isn't the only thing. Sampling rate matters too. If you sample too slowly, you get aliasing, a fancy word for when your readings lie to you. It's like watching a wagon wheel in an old movie. It looks like it's spinning backwards because the frame rate is too low. In electronics, if your sampling rate is less than twice the highest frequency in the signal, you'll miss important details. This is why the Nyquist rule says, sample at least twice as fast as your signal's top frequency. ADCs aren't perfect. You'll run into errors like noise, random fluctuations that sneak into your signal, offset error when the ADC always reads a little too high or too low, reference voltage issues. If your ADC's reference voltage isn't stable, your readings will drift. Knowing these limitations is key to designing accurate measurements. One simple trick to fight noise? Average multiple readings. Take 10, 50, or even 100 samples, add them up, then divide by the number of samples. This smooths out random fluctuations and gives a more reliable value. A trick used in everything from digital thermometers to industrial sensors. So next time you need your microcontroller to read the real world, remember, choose the right resolution, pick an appropriate sampling rate, watch out for errors, and when in doubt, average it out. That's the power of ADCs, turning the chaos of analog signals into clean, usable numbers your code can work with.